Lab 3 revolves around black holes and their gravitational forces interacting with their... Black holes are stellar masses of incredible magnitude, resulting in a gravitational force strong enough even to cause stars to orbit them. Much is still unknown about such black holes, but in this experiment we will determine the mass of one given observed data regarding an orbiting star. Unlike other labs where the object's motion was predicted using initial conditions, in this lab we are using an object's motion to determine the mass of another object using fundamental principles. The purpose of this lab is to use physics concepts such as the momentum principle and modeling to determine the mass of a black hole. Through the experiment, we determined the mass of the black hole given our initial conditions provided by WebSign to be as is seen on the screen. Some of the initial conditions were provided by WebSign, particular to this individual model, and can be seen here as how they incorporate into the model created. The star's mass, for instance, is placed under the system properties and will be used for determining various forces and their impacts, as well as the mass of the black hole in the final computation. The time step, notice, is recorded in seconds, as that is the standard SI unit, and the black hole position. The position will be used in order to find r hat for some various calculations, as well as for finding the final mass. So the equations use the fundamental principles. The big ones are the momentum principle, that dp dt, the change in momentum in relation to change in time, is equal to the net force. That is not to say that they are the same, as they are made of very different components, and that will be touched on near the end of this video. The net force is equal to g, the universal gravitational constant, which is approximately 6.67 times 10 to the negative 11th, times m1 and m2, that's the mass of your two bodies, and r squared is the square of the distance. This equation can be written to solve for the mass of the black hole, as is seen here. This is just a rearrangement of that algebraically to solve for one of the individual masses. So now let's take a look at the Python code used to create this model. I've already touched on the initial conditions that were set up. This section is drawing in the velocity data from the CSV file provided by WebSign. So where all of the actual physics computations are completed is in this calculation loop. Here you will see the initial and final momentums are computed by multiplying the star's mass by their velocity at that point, as momentum is mass times velocity. The change in velocity is computed by subtracting the initial velocity from the final velocity. Change in momentum is computed by subtracting the initial momentum from the final momentum. dp dt is calculated by dividing the change in momentum delta p by the change in time delta t, and those values will change with every iteration of the loop for each different index and position of the star. The net force is equal to the dp dt. This is the vector. Two vectors are equal, as was touched on as the momentum principle. P hat is the direction of the momentum, the current instantaneous momentum. As you see, that is the momentum p initial divided by the magnitude of the momentum. The parallel component of dp dt can then be computed here. As you see, it is the change in the magnitude of momentum over the change of time. That is the parallel component of dp dt. The perpendicular component, which is then summed with the parallel component to find dp dt, can then be computed as we know dp dt and we know dp dt parallel. So you subtract the parallel component from the total to find the perpendicular component. R, the distance between the two, can be found by taking the magnitude of the black hole's position minus the star's position, as well as the gravitational constant is put in here in order to calculate the mass of the black hole, which is then computed using the gravitational force equation earlier solved for black hole mass. So when this is run, and pause in any instance, you can see that there are three arrows, the blue representing the perpendicular component of net force, the black representing the parallel component of net force, and the yellow representing the total net force. In the console window, you can then see, as was specified to print in the code, the mass of the black hole, which was found to be 1.97 times 10 to the 31st kilograms. This is reasonable, as it is markedly larger than the mass of the star provided, as you would expect from a large black hole with a star orbiting around it. One of the provided questions was the comparison of FNet and dp/dt. While yes, they are equal, they are very different by their components and tell us very different things. dp/dt is made of dp/dt parallel, which indicates whether the object is slowing down or speeding up, and dp/dt perpendicular, which determines whether it is turning left or right. FNet is made of FNet parallel, and F net perpendicular, which show the direction of the forces. F net perpendicular points to the center of the kissing circle when an object is turning. What if, imagine the black hole was removed and a different black hole was placed in the same location. Assuming that the observed motion stayed the same, the mass of the new black hole would have to be equal to that of the old black hole. Otherwise, there would be a different net force and a different motion of the star. So in conclusion, we use modeling and the fundamental principles to determine the mass of the black hole.